What's up, everybody? Welcome back to another live stream from the Scalar Learning channel. And today we are back with our next J.E.D.I digital SAT training class. Okay, we are on math class 4 of 7, which is really exciting. And for everybody who is on right now, thank you for joining. Welcome, welcome. Just making sure everything is running smoothly. Yes, okay. Okay, perfect. So, welcome back. This is a very important lecture, so I'm sure a lot of you guys who are really shooting for the stars here know that this is an important one to make because we're on the advanced math, okay? And if you guys haven't seen the Everything You Need to Know About the Digital SAT video yet, I highly encourage you to watch that. That was in week 1, but we talked about all the different subcategories in the advanced math category. There's actually 13 in particular, so we're going to kind of go through all of the critical concepts for these 13 subcategories. You guys are welcome to ask questions. That's the benefit of joining live. So if you do have questions, just post them in the chat. What's up, Cole? What's up? Is that Muxita? Welcome. And do you think SAT Panda is good for practice problems? So check it out. I used to think it was amazing for the old version of the SAT. I actually haven't seen the SAT Panda stuff for the new digital SAT. I have to check it out. I will say that in the past, they've done a phenomenal job, but I need to check out the new platform, and honestly, I haven't yet. So if they do have new resources up for the digital SAT, that is amazing. And by the way, let me know in the comments real quick as we get started, what do you think so far of this class and the school platform and all the resources that we've posted thus far? Just let me know. Do you like it? Are you finding it useful? Is there other things that we could add? The other thing before we get started too, I'd love to know where everybody's tuning in from. So you can just post where you are in the world. You can just say your country, your state, or city, or whatever you're comfortable with. I'd love to know. That'd be super cool just to hear where everybody's from. Okay, without further ado, let's get into this advanced math. This is really, really important stuff, and we will jump around to questions as time permits as well. What's up, Jaden? You're welcome. Very helpful so far from Florida. Amazing. Thank you. Oh, that's amazing. Jaden said you've been helping me like crazy. Hello, Iwan. Nice to see you. All right, let's keep it going. By the way, should mention, if you guys haven't joined the school community yet, I do like to mention it at the jump of every one of these. Make sure to join our school community. There it is. Everything is totally free and totally awesome. It's the best online free course out there, probably best online course period, but we are also offering it for free, so that's an added benefit for those of you folks who are looking for something free, so make sure to check that out. I just posted it in the chat, so click that link, join our community. We're getting close to I think like 250 members, which is super cool, and I think it's going to keep growing and growing as we get closer to the SAT. From Morocco, amazing. Okay. So, Cole, you mentioned the adjustments to College Board Test 1, 2, and 3. So, somebody else mentioned this, and I haven't yet. But as we get closer to the test date in August, I'm going to redo those practice tests. So, I'm going to redo the adjusted practice tests, and then I'll check out everything at that point. But that's amazing. Okay. Osama, what's up? All right, here we go. Starting off. This is in order based on the Khan Academy ordering of topics. Okay, so first we have factoring, quadratic, and polynomial expressions. Okay. So first of all, what is factoring? So if we have an expression like this is a binomial and it's a quadratic because the highest degree is 2. When we're talking about factoring, we're factoring out what both of these terms have in common, which in this case is x. So it would look like this, right? This is just factoring out a single factor, x times x plus 2, it's equivalent. Now we have something like this, which is a quadratic, and we're going to get into more details eventually on like how to factor a quadratic specifically. But what we're doing here is a way we'd factor a quadratic, just as a general overview, is that one would be factored into 2 binomials, x plus 2 times x plus 5. Now there's a methodology and a reason behind this, like why we're factoring it in this way, and it's sort of the reverse of foiling, meaning if we were to recombine these, oh, what's up, from Ghana, super cool. And yes, Jaden, I will be doing the new practice test live or with the adjusted problems. And then again, as we remember to FOIL, which I've talked about in a previous video, x times x is x squared, x times 5 is 5x, 2 times x is 2x, 2 times 5 is 10, and you combine the 2x and the 5x, and you come back to that original polynomial. And then last but not least, we have a cubic function. Now, I haven't really seen a lot of these on the digital SAT, so just take that into consideration when I show you, but these are factorable. So this one is factorable into these different binomials, but I'm going to also show you how to factor sum and difference of cubes later on. where it becomes a little bit more feasible. But again, I haven't really seen that at all on the digital SAT. So I'm going to show you how to do it just in case, but I'm giving you that caveat that I just don't think it's super critical anymore. What's up from Pakistan? Amna, welcome. All right. So factoring quadratics, how do we factor a quadratic like this, right? Typical quadratic, no leading coefficient, by the way, just or a 1 as a leading coefficient. So the first question you got to ask is what multiplies to that last number? Notice how I said -6, not 6, right? Because the minus always sticks to the number on the right. And what adds to 5? So go ahead and think about that. What two numbers multiply to -6 and add to 5? Put your answer in the chat when you got it. Multiplies to -6 and adds to 5. Two numbers. Two and 3 multiply to +6, not -6. But then I see Cole in the mix. He's got a 6 and a -1. Those do multiply to -6, and they do indeed add to +5. So let's check it out. It is 6 and -1, and that's how you factor it. You just break it up as follows. X plus 6 because it's +6. X minus 1 because it's -1. Boom, done. Okay, moving along. Now we're going to talk about the star method. Again, I haven't had to use this a ton on most of these practices. Good job, Iwan, Osama, and Anna. But I'm going to show it to you anyways in the event that a leading coefficient comes up like this. And when I mean a leading coefficient, I mean that number in red, right? That 8, that's our leading coefficient for the leading term. So how do we factor a quadratic with a leading coefficient? We can't just say what multiplies to -3 and adds to 2. Now that 8 throws a wrench in the tire. So I'm going to show you my favorite method, which is the star method, where you make this little star and you put A times C at the top, A and A to the left and the right. Notice how everything's color-coded. Then Y1 and Y2, which we got to figure out what those are, and then B on the bottom. So what does that look like with this expression? Well, up top, 8 times -3, that's A times C. Left and right is 8 and 8, right? And then on the bottom, we have 2, okay? So that 2 is the B term. All right. So now what do we do with this? Well, we know that 8 times -3 is -24, and we're trying to figure out two numbers that multiply to -24 and that add to 2. Two numbers that multiply to -24 and add to +2. And that's right here. It's kind of abbreviated out, right? What multiplies that A times C, what adds to B? And that would be -4 and +6. Those multiply to -24, you add them together, you get +2. Now what we're going to do is we're going to reduce these like fractions, meaning the 8 over -4 and the 8 over 6, right down here. We're going to reduce those just like we would a fraction of 8 over -4, which would reduce to +2 over -1. Notice how we would normally say, hey, that's a -2, but keep the negative on the bottom where it was at the beginning, keep the positive on the top, and the other one, 8 over 6, reduces to 4 over 3. Now those go into the following factored form. Notice the 2 on top goes with the x. The -1 is a standalone constant. The 4 goes with the x on top. And the bottom number, again, is a standalone constant, 3. And we've got 2x minus 1 times 4x plus 3. We've got Lester saying the new questions that were introduced in the practice test from College Board can be found in 2 Delaney test work. Oh, yeah, that guy's a legend. He's a buddy of mine. Cole's a trader. Nah, it's all good. That guy's cool. The video came out a few days ago. Okay, awesome. Scalar only. What's up, Cole? That's what I'm talking about. Loyalty. All right, moving along. Now we've got, oops, I messed up my animations here, so excuse me, but we're going to get to that at the bottom. All right, so now we're going to talk about factoring sum of cubes and difference of cubes first really quickly. Again, as I mentioned, I haven't really seen this much, but I'm giving this to you in case it does pop up. So x cubed plus b cubed, that is a sum of cubes. And the way you factor it is take the cube root of the first term, x, the cube root of the second term, b, and you make it x plus b. So if it's a sum of cubes, you start with x plus b. Then you take that first value term, x, and you square it, x squared, minus the product of these guys, and then plus the last one squared. So the nice thing to remember, if I'm trying to remember the signs, same, meaning if it's a sum, it's plus. Different, if it's plus, then it becomes minus. And then always ending with plus. An example here, x cubed plus 27. 27 is 3 to the third power. That's why it's a sum of cubes. So again, x plus 3, right, that's my b. Then x squared minus the product of 3 and x. And then plus 3 squared. And a difference of cubes, okay, It's, oops, this should be, sorry, this should say, oops, hold on. This animation is wrong. Let me fix this for you guys real quick. Hold on. This should say minus right here. Let me fix that. Boom, 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 and boom. All right, we're going to get back in the mix now. Hold on. And let's add an animation here. So this animates properly now. Hold on, give me 1 second. All right, here we go. So now we're into difference of cubes. So that is a difference of perfect cubes, x cubed minus b cubed. And again, we have that same breakdown, same minus, different, plus is different than minus, and then plus at the end. And now if we get an example here, cube root of 8x cubed is 2x, cube root of 27 is again 3. And then we get the first term 2x squared, which is 4x squared. The product of 2x and 3, which is 6x. And then we have the last term squared, which is 9. We got a question here. For the star method, can you just use the quadratic formula? Yeah, you can use the quadratic formula if the goal is that you're trying to just find the zeros of that quadratic. Absolutely. In certain cases, they're going to ask for the factored form or something like that. So that's also why you might still, even if you know the quadratic formula, you might still need to know how to factor a quadratic. But I will mention that once again, I don't recall seeing too much on this digital SAT in terms of factoring with the leading coefficient other than 1, but I wanted to give it to you just in case because it is fair game. All right, topic number 2, radicals and rational exponents. So we're going to talk about radicals, and the most common radical is a simple square root, meaning that radical symbol without any little number there, right? And so what is the square root asking? It's asking what number times itself equals this number under the radical. Square root of 4, therefore, is 2. Square root of 9 is 3 because 3 times 3 is 9, and so on and so forth, right? So when we look at these exponents of variables, square root of x squared is just x because x times x is x squared. Square root of x to the 4th is x squared. And what you might notice is for the variables, as we're taking the square root, it's like we're dividing the exponent by 2, dividing it by 2. Once again, 8 dividing by 2, and so on and so forth. What about cube roots? Okay, cube roots are asking what number times itself and then times itself again equals this. So cube root of 1 is, of course, 1 times 1 times 1 is 1. Cube root of 8, that's 2 times 2 times 2. 27 is 3 times 3 times 3. And so on and so forth. Now, if we look at variables, what are we doing for those exponents? Instead of dividing by 2, which was the index for a square root, it's just invisible. We're dividing by 3. Cube root of x cubed is x. Cube root of x to the 6th is x squared, right? 6 divided by 3 is 2, and so on and so forth. So these are the most common ones. You could have 4th root, you could have 5th root, you could have 10th root, but this is typically what you will see. All right, so how do we simplify these roots or these radicals? Let's take an example here. Let's take a square root, right? So we got a square root of 32 x cubed y to the 6th z to the 9th. Sometimes you will have to do this on the SAT, and you're going to have to simplify these radicals. So the question is, how do we do that? Well, it's a square root, so we're trying to, when we're simplifying, we're basically saying how many things can we pull out of this square root within, the bounds of what's allowed. Well, the only thing that can come out of a square root prison is perfect squares. There are perfect squares, right? 32 is not a perfect square, but it's got some perfect squares in there. Well, it's got 16, right? So 2 times 16 is 32. X cubed is not a perfect square. Excuse me, but again, it has a perfect square in it, x squared, because x times x squared is x cubed. Y to the 6th is a perfect square. You may not agree with me, but I'm going to show you why in a second. Z to the 9th has z times z to the 8th. Again, z to the 8th is a perfect square. You might be like, wait a minute, 8's not a perfect square, and that's true. But z to the 8th, or a variable to any even number, is a perfect square. I'm going to show you why in a second. So now we're going to start simplifying by taking out the perfect squares, meaning taking the square root of all these perfect squares. Square root of 16 is 4. That comes out. Square root of x squared is x. Why? Because x times x is x squared. Square root of y to the 6th, that's y to the 3rd. So why is that? Because again, y to the 3rd times y to the 3rd is y to the 6th, because when you multiply variables, you add the exponents, right? And we got the square root of z to the 8th, that is z to the 4th. So notice we're basically dividing by 2. We're dividing by the index. Square root has an index of 2, dividing by 2. What's left inside the radical? Everything else. 2, x, and z. What about if we're simplifying a cubic root? Okay, you're going to do the same thing, right? Notice that little 3 is the index. So we're taking a cubic root. So again, we're going to try and find the perfect cubes. And I know there's a perfect cube in 81 because it's 3 times 27. 27 is 3 times 3 times 3. Cool. What about x to the fourth? Yes, it's got a perfect cube in there. X times x cubed. Obviously, that's a cube, right? Y to the sixth. That's a perfect cube. Why is that? Because the exponent is divisible by 3. Remember, x squared times x squared times x squared is x to the sixth, okay? So we're looking for multiples of 3, really, in those exponents for perfect cubes. Last but not least, for the z to the 11th, we got z squared times z to the 9th. So again, that z to the 9th, 9 is a multiple of 3. It's a perfect cube. Now let's take the cube roots. Cube root of 27 is 3. Cube root of x cubed is x, because x times x times x is x cubed. Cube root of y to the sixth is y squared. Huzefa said he's leaving this question alone. No, it's very doable. It's very doable with some practice. And then the cube root of z to the 9th is z cubed, right? 9 divided by 3 is 3. And what do we have left inside? We have the 3, we have the x, and we have the z squared. So there you go. That's how we simplify radicals. Okay. Now, what about denominators and rationalizing denominators? First of all, what does that mean? So we're talking about a rational expression with a radical in the denominator. We don't like that. The College Board doesn't like that. Mathematicians don't like that. So we want to get that radical out, but you can't just get rid of it, right? We have to still keep the value of the expression. So this is where we're going to be simplifying the radical by getting rid of that radical 5 in the denominator by multiplying by rad 5 over rad 5. When you do this, you get 3 rad 5 on the top, but the beauty is, what do you get on the bottom? Well, any radical times itself just kills the radical, becomes that number. Why? Because rad 5 times rad 5 is rad 25. Square root of 25 is 5. Okay, same with any number. So we get 3 rad 5 on the top, and as I mentioned on the bottom, it just becomes a nice 5, which has been rationalized, and that's it. But what about when we get a crazy thing like 4 plus rad 5? Okay, what do we do? So shout it out in the chat. What do you think we got to multiply by here? And you can even say one word. You don't even have to say the binomial. You can say the word, which begins with a C. Cole says, what if the denominator is 3? What did you say? Hold on. Oh, yeah, I think you retracted it. Okay, never mind. Yeah, shout it out. Anyone know that C word that we have to multiply by here to rationalize this denominator? Waiting to see if somebody's got it. All right, well, I guess I'm going to have to tell you guys. Multiply by the conjugate. What's the conjugate? The conjugate, okay, oops. The conjugate is the same thing, 4 plus rad 5, just minus. 4 minus rad 5. You see that? So now we have 4 minus rad 5, but I got to do 4 minus rad 5 over 4 minus rad 5. Why? Because that's 1. And that means if you multiply by 1, you're not technically changing the value. Oh, Cole says he forgot how to do this. Well, perfect. All right. By the way, if you guys could click that like button right now, it would be a tremendous, tremendous help. Really appreciate it. Helps the channel massively when you guys do hit that like button. So if you could, I'd appreciate it. Okay, so we multiply it out. Now, on the top, you're just going to distribute, right? You're going to get 12 minus 3 rad 5. But on the bottom, something very interesting happens. You get 16 minus 5. Why? Because as you FOIL this out, because remember, you have to FOIL, you get 4 times 4, which is 16. Then you get 4 times negative rad 5, negative 4 rad 5. Then you get positive 4 times rad 5. Negative 4 rad 5, positive 4 rad 5. They add together. They get 0. They cancel out. So you're good. And then you get rad 5 times negative rad 5. Again, the radicals destroy each other, as I mentioned. And we get minus 5. Now, there's no more radicals on the denominator. We just simplified to 16 minus 5, which is 11. And we are left with 12 minus 3 rad 5 over 11. Boom, done. Thank you for all those likes, guys. Really appreciate it. Okay. Moving on. Now we are talking about rational exponents. What's a rational exponent? That is a fraction exponent. So what the heck does 8 to the 2/3 even mean? Well, I'm going to tell you. The 2 on top is what I call the power, or the exponential power, the typical power, right? So it's really meaning you're raising 8 to the second power. What about that 3 on the bottom? That is your root, meaning you're taking a cubic root, okay? So how can I evaluate this? We're taking the cubic root of 8 squared. Or you can take the cubic root of 8 squared. Both are going to give you identical results. Which way is easier? The second way. It's easier to go small than big than small, right? Because 8 squared, 64, it's a pretty big number. What's the cubic root of 64? Okay, maybe you can figure it out that it's 4, but not as easy as instead saying what is the cubic root, and by the way, Cole, yes, you got it. What is the cubic root of 8? That is 2, right? Smaller number, easier to get that answer. 2 times 2 times 2 is 8. What's 2 squared is 4. So now I'm going to show you how we do those written out, right? Same thing, cubic root of 64, which is 4. Or the cubic root of 8, which is 2. 2 squared is 4. Same answer, done. Oh, and by the way, you know, this is how you can go back and forth, right? If you see the cubic root of 8 squared, you can rewrite it as 8 to the 2/3. So sometimes you're going to have to go back and forth between these different abbreviations. That is definitely coming up a lot on this new version of the digital SAT. Okay, what about multiplying and dividing exponents? So what do we do? We've talked about this in the formulas video. When you multiply with the same base, you're adding those exponents. So we're getting x to the 11th in this example. When we are dividing by the same base, x and x, right? We're now subtracting those exponents, and we get x cubed in this case. Now, what about when we add and subtract variables, with different exponents? Nothing. Cannot do anything. When you're adding those are like different terms. That's like adding x and y. You can't do it. They stay separated, right? Same with subtraction. No difference there. So just want to give you that heads up. There's nothing we can do in those situations. You're kind of stuck. Okay. And when we talk about exponents, what about negative exponents? I'm not saying that I'm seeing this a ton on the SAT when you're having to deal with negative exponents, but I want to go over it just in case it does pop up. So x to the negative 7th is simply the same as 1 over x to the 7th. Anytime you have a negative exponent, it just means it belongs in the denominator. But what about when you have a negative exponent in the denominator? Now the reverse is true. So like, how would I simplify this expression? 8 over 2 simplifies to 4. That we already know. But what about that x to the negative 3rd in the denominator? Well, I always say negative, it's in the wrong spot. If it's in the numerator, it belongs in the denominator, and vice versa. So that means it's just 4x, and then that x to the negative 3 comes up to x to the positive 3 up on the numerator. So now there's no denominator, right? 4x times x cubed, and then we simplify that. X to the 1st times x to the 3rd gives us x to the 4th. Boom, done. That's how we do it. All right, moving on to subcategory 3 operations with polynomials. So what is a polynomial? A polynomial are these multi-term expressions, right? So x cubed plus 2x, that's an example. This is a trinomial, another polynomial. 4x squared plus 7x minus 3. And then we have this gigantic one. So this is, with 5 terms, but these are all polynomials. Poly meaning many. You can also have a monomial, which is just one term, 3x to the 6th. And again, here's a binomial with that terminology, 2x to the 4th plus 7. For this last one, we might just call it a 5-term polynomial. There's a name for it. I can't even remember. But for a 4-1, what is that? Trinomial, quadrinomial. I think it's a quadrinomial, and then the 5th, I can't remember. But you don't need to know it. Okay, great. Moving on. Adding and subtracting polynomials. So how do we add and subtract polynomials? So first of all, we're adding these together. So my first question to you is, do the parentheses even matter when it is, oh, Chris, you have a doubt? What do you mean? So let me know what you're asking about. So these parentheses are irrelevant when we're adding, so I can pretty much just destroy them, get rid of them, okay? And then I'm going to add all of my like terms. Those are my x squareds. Those are my single x's, and here are my constants, all right? So what's 3x squared plus 4x squared? That is 7x squared, right? You're just basically adding those coefficients, 3 plus 4. What about negative 2x plus x, right? That's like negative 2 plus 1. Again, adding those coefficients, and that gives us a negative x. And then 2 and negative 5 gives us a negative 3. So that's how you do it. What about subtracting these polynomials? Now, the parentheses on the second expression do matter, right? Because that means we have to distribute that negative. So notice, 4x squared becomes negative, x becomes negative, 2 becomes negative. But now it's the same dealio, right? Combine like terms, 3x squared minus 4x squared, negative 2x and negative x, and negative 5 and negative 2. So as we combine this, 3 minus 4 is negative x squared. Negative 2x, negative x is negative 3x, and negative 5 and negative 2 is negative 7. All right. And now what about multiplying polynomials? All right. So you guys know about foiling. When we're foiling two binomials, now this is foiling a binomial and a trinomial. Still the same principle, but a little trickier. By the way, Cole's got a question. When typing in answers for the digital SAT, if there are decimal spots, what you round to? Great question. The standard protocol for the SAT is rounding to the thousandth, I believe. And I think they put that in on the free response on the left, so you can see that. And you can round to the thousandth, but excuse me. Just double check that when you're taking a practice test for that little sheet on the left. All right, great question. And by the way, a lot of times if I can avoid rounding, meaning entering the fraction instead, I do it. I like to do it because I feel safer with it. But yeah, if you need to round, that's this protocol. All right, multiply. You're welcome. Multiply these guys. So how do we do this? Well, just like that 2x in foiling, we'd multiply the first two terms. We're doing the same thing here. So it's first times first, which gives us 8x cubed. Then we're going to stick with that 2x. It's got to go down the line. Again, it's got to multiply the next one in the trinomial. That gives us 2x squared, and then 2x times 2, which is 4x. Now look how I'm stacking it with a binomial times a trinomial. I'm starting off with the next negative 5 times 4x squared, and I'm placing it underneath. Oh, no, actually, never mind. I usually like to place it underneath the 2x squared. Here, I'm just doing it linearly, I think, for the sake of this example. But when I'm doing it on the test, I like to put this underneath the x squared so I know what's going to combine. It's all like right there. But anyways, so then we got negative 5, and now we're going down the line times 4x squared, negative 20x squared. Negative 5 times x, negative 5x. And negative 5 times 2 is negative 10. Now we're going to combine all the like terms. 2 and negative 20 is negative 18. 4x and negative 5x is negative x. And these two on the end have no like terms. That's how you do it. Done. Okay. Now we're going to talk about something that I haven't really seen tested much on the new digital version. I did see it on the old version, the paper version, but I'm putting it on here because I do think it's fair game. And we could see it coming up, especially as they are kind of modifying and updating the test in real time. So here we go. We are going to give you an example, right? We've got x cubed plus 4x squared minus 3x plus 1 divided by x minus 1. So how would we do this using synthetic division if this does come up? Or we might see an expression, the first polynomial over the bottom one. So the way we do synthetic division is we take those coefficients of the first polynomial, and then we take that value in orange, but we negate it. So it's a negative 1 there. We're going to put a positive 1 in a box out here. And this is going to go through, and now we're going to basically be able to divide by x minus 1 like so. So we're going to drop that 1 first, and then multiply by that 1 in the box. Put that product right here. 1 times 1 is 1. Then we're going to add, what's 4 plus 1? 5. Then we repeat. 5 times that 1 gives us 5. We add it here. Add negative 3 plus 5, and that gives us 2. Repeat one more time. Multiply, and put the product 2 times 1, which is 2, right here. 2 plus 1 is 3. So what do we got now? Well, since it started as x cubed, we move it down by 1 degree. And this is the coefficient of not x cubed, but x squared. This is the coefficient of x. This is the constant, and then this is our remainder. So let's see what that looks like for our final simplified polynomial. So we have 1x squared plus 5x plus 2 plus our remainder. Wait a minute. Why do we put the remainder over this? Because this is the divisor. This is just like if we're dividing a number by another number. The remainder is really our fractional remainder, and we get the full fraction by throwing that over the original divisor. So it's the same thing here. No different. Okay. Next, we have a long division method of dividing polynomials. So this is another example where we're dividing, and this is really useful, long division in particular, when we have a leading coefficient like this, like a 2x, as opposed to in the last example is just like x minus 1. So this is going to be problematic. I mean, you can still do it with synthetic, but you have to modify it a little bit, but long division is going to work great. Long division is just straight up long division, like we remember right back in the day when we had to do it in earlier levels of math class. It's really cool. So all we're going to focus on is this leading term. We don't even worry about the negative 1. And we look at the degrees over here, right? So first we're like, how do I get 2x to be 4x cubed? Oh, well, I multiply it by 2x squared. right? That's going to multiply that, and we're going to get 4x cubed. 2x squared minus 1 is negative 2x squared. Now, just like regular long division, we have to subtract this bottom expression. So notice that's going to be negative, and this one is going to flip to positive because we're negating the entire binomial. Then we're going to combine these, add them together essentially. Those are going to cancel out, and then we got 6x squared. Now we're going to drop the negative 8x and do it again. Again, only looking at the 6x squared, not even worrying about this. What times 2x gives us 6x squared? That is 3x. Okay, so 3x, now we got 6x squared, and then 3x times negative 1 is negative 3x. Again, we're subtracting. So we're going to negate, and then combine these together. And those are going to cancel out, and we're left with negative 5x. Last one, we're going to bring down the 1. Again, just like traditional long division. What's going to make 2x get to negative 5x? Multiply it by negative 5 over 2. Negative 5 over 2 times that gives us negative 5x plus 5 halves. And then we've got to negate, add these together, and the 5x's cancel out, and we're left with negative 3 halves. So our final answer now is all of this, what we have up here, with that nice little remainder, negative 3 halves, over the divisor. And then you can just simplify by throwing that 2 in the denominator like so. There's your long division. So again, have I seen a lot of this or synthetic division? No, I haven't. And I would rate it lower down the totem pole in terms of what you need to know, but I'm just putting it out here just in case, okay? Cole says, I'm scared for August. I hope they don't modify anything too crazy. I just want to get it over with. I hope so too. All right, now we're on to topic 4, operations with rational expressions. So rational expressions are things like this. It's like something over something, okay? So how do we simplify a rational expression where we're dividing two different rational expressions? So I'm going to walk you through the process. So we have this divided by this. First of all, when we're dividing, we need to implement keep, change, flip when we're dividing two fractions. Keep the first one, change this to multiplication, and flip the second one. The next step is factor as we simplify. So again, this polynomial on the top left, it's got a leading coefficient. You need to use star method. I'm not going to go through all of star method right now. Again, but using star method, you're going to get this beautiful binomial times binomial, 3x minus 5 times x plus 1. The denominator, we're factoring out greatest common factor, which is x. 3x stays as is. On the bottom here, we can factor out a 3, right? And we get 3 times 3x minus 5. Oh, wait. Oops. That should be 3 minus 5x. Hold on. 3x. Oh, you know what? I can fix this really quickly. Hold on. We're going to fix this in real time. That should be 9x. There we go. That was a little mistake. 9x minus 15. There we go. We are back. Making changes on the fly. All right. So there you go. That was a little mistake. My bad. 9x minus 15, 9x minus 15. And then you factor the 3 out of that, and you get 3 times 3x minus 5. Okay. So now we have this great example. And then now the question is to simplify. Well, what do we see that we can cross off? And that's what the simplification process is all about. Well, I see a 3x minus 5 on the top and bottom. Goodbye. I see a x plus 1 and x plus 1 on the top and bottom. Goodbye. I see an x on the top and bottom, and I see a 3. And when everything cancels out, meaning the top and the bottom are exactly the same, we're left with 1. Okay? So in this case, this whole thing, sorry, give me 1 second. I'm just trying to see something on my screen. This whole thing then moves to 1, and that's how you get it. Boom, done. Okay. Now we've got another example, but here we are subtracting two rational expressions. Now, this I've definitely seen on the new SAT, ones just like this. So you definitely got to know how to do this. So check this out. We need to get, 1 second. We need to get common denominators here, okay, in order to combine these. So for example, we have 3x minus 5 and x plus 7. So how do we get common denominators with these rational expressions? Well, the way we can do it is we've got to multiply this second denominator times the first and this first denominator times the second. And again, we have to do it as x plus 7 over x plus 7 because then it's 1. And for the other one, 3x minus 5, 3x minus 5. And now we can simplify a little bit once we have common denominators. And that's what they're really going to ask you to do a lot of times. Hey, they'll say which expression is equivalent to this? And they're talking about simplifying, getting common denominators and combining. So as we distribute this 3 on top, we get 3x plus 21. Here we get 15x and 25. But notice that minus has got to go with it. So we're going to talk about that in a second. So check this out. As I mentioned, we got 3x plus 21, and that's really a negative 5 being distributed. Therefore, we get negative 15x and positive 25, right? All right, now we're going to combine like terms. 3x minus 15x is negative 12x. 21 plus 25 is 46. And we are left with negative 12x plus 46. And notice I didn't FOIL the denominator. I could have FOILed it out, but usually in the SAT, I'm noticing they don't do that, so I left it as is. Now we are on to nonlinear functions. So again, nonlinear functions, it's anything with basically for the purposes of this test, either a rational function or something with an exponent greater than 1. So x squared, x cubed, x to the fourth, etc. So these are all different examples of nonlinear functions. And notice that function notation, right? The letter is arbitrary. It can be f of x, g of x, h of x, whatever it may be. And we might have different things that they're going to ask us to calculate. So for example here, right, we've got f of 2. So we need to be familiar with what does this mean when they're saying find f of 2. Oh, that means we're plugging 2 in for f of x. So I'm replacing the x with 2. 2 cubed is 8 times 3 is 24 plus 7 is 31. So this is some good function notation to have in the, oops, I didn't mean for that to go away. Hold on. And then now we've got g of 2. How would we do this? Same thing. Plug and chug 5, 2 to the fourth. 2 to the fourth is 16 times 5 is 80. And then, hold on, I need to see how I can flip to the next one without losing this. There we go. And then we want h of negative 2. So again, now I'm plugging in negative 2 for x, for the h function. Negative 2 squared is 4 plus 3 equals 7. And that's how you do it. All right. Whoops. Clear that. And let's close it. All right, let's move on. So now we have another example of different f, g, and h. And now we're going to talk a little bit about some more detailed function notation. Okay. So with this function notation right here, we have f of 1 plus g of 3. So that means we have to evaluate f of 1 cubed, and we have to add it to g of 3, and g has it to the fourth power. I'm going to try and do this somewhat mentally. 1 to the third power is 1 times 3 is 3 plus 7 is 10. 3 to the fourth power, I believe, is 81 because 3 times 3 times 3 is 27 times 3 is 81 times 5 is 405. And we add these together and we get 415. Okay. Next. Hold on. Let's go to the next one. Now we've got g times h of negative 1. So what is this? This is really saying g of negative 1 times h of negative 1. So what is g of negative 1? Plug in negative 1 here. Negative 1 to the fourth is 4 times 5 is 5. And then we want times h of negative 1. Plug in negative 1 here. Negative 1 squared is 1 plus 3 is 4. 5 times 4 is 20. Okay, last but not least, we have, hold on, I need to move this. How do I move this thingy? All right, it's not letting me move it. 1 second here, let me close it for a second. So you see this open circle, this is function composition, okay? So this means h of g of negative 2. The way I like to rewrite this is h of g of negative 2. That's an easier notation, and it still means the same thing. So this tells me I first need to find g of negative 2, so I'm going to plug in negative 2 in here, right? So negative 2 to the fourth power is 16, because any negative to an even power is going to be positive. 16 times 5 is 80. So then now we're trying to find h of 80. And that would be 80 squared is 6,400 plus 3 is 6,403. So that's how you do it. All right. And we're going to talk a little bit about transformations, because this is something that is coming up a lot. F of x minus 2. So what does that mean when you see, so like sometimes it'll be like, hey, this is the function f. What are the x-intercepts of f of x minus 2? So you might be like, oh, I just moved the x-intercepts 2 to the left, but that is incorrect, okay? When it's x minus 2, you're actually going 2 to the right. You're shifting it 2 to the right. X plus 7, again, you might think 7 to the right. That's incorrect. It's actually 7 to the left. When you have function notation like this, f of x minus 2 and the minus 2 is outside the parentheses, you're going 2 down. And if you had plus 7 on the outside, you're moving 7 up. So these are good little things to note. By the way, you can always verify these using Desmos if you're unsure. There's really cool ways you can type in a function like f of x equals whatever the function is. And then in a second line, you can type in f of x minus 2 and see what happens. And you'll see in real time, oh yeah, minusing 2 actually shifts it to the right, not the left. Oh, did I lose you guys on where I got 80? Hold on, let me back up. Where did I get 80? Oh, for G. Here, let me show you. Let me write it out. So again, we have h of g of negative 2. Okay, maybe I made a mistake, but let me double check. So g of negative 2 is 5 times negative 2, replacing the x with negative 2 to the fourth power. So what is negative 2 to the fourth power? Negative 2 times negative 2, which is 4, times negative 2, which is negative 8, times negative 2, which is 16. And then 5 times 16 is 80. So that's where I got the 80. So let me know if that makes sense for you guys. Okay, let's move it back to here. All right. And we talked before about factoring polynomials. Why is factoring these polynomial functions or these other nonlinear functions so important? It's because it helps us find the zeros of these functions. So for example, when we go back to this one where we factored it to x times x plus 2 as a function, okay, this means that we can figure out whenever this is going to go to 0. And it's going to go to 0 when that goes to 0 or when this binomial goes to 0, meaning at 0 and negative 2. Another example here, when this is factored, we know our zeros are where each of these zero out. So we have a 0 at negative 2 and negative 5. Last but not least, for this gigantic one where it factors to this, we now have 3 zeros, right? We have what makes this 0 out, and this 0 out, which is 1/4, right? 1/4 times 4 is 1 minus 1 is 0. 2 minus 2 is 0. And 3 minus 3 is 0. Okay. Topic number 6, isolating quantities. This is one of my favorite categories because you don't really have to do much in terms of understanding the setup of the question. All you got to do is be like, oh, I recognize the isolating quantities question. I'm going to isolate the quantity. Done. Don't even think about it. So for example here, right, we've got this function. Or formula, I should say, a equals 1 plus x over 2x, and we're trying to isolate x. Now, depending on the equation and the setup, it's always going to vary, but let me just show you the general protocol. What are we trying to do? We're trying to get x by itself. Now, I did choose kind of a hard one because we got an x on top and the bottom, and you cannot cancel out the x's. Don't make that mistake. But we start when there's one of these in the denominator by multiplying it to the other side. That's our beginning step, right? So we're multiplying both sides by 2x, but it just cancels out on the right-hand side. And then we're left with 2xa equals 1 plus x. I need to get the x's together. I need to consolidate. Always think that. So I'm going to minus x from both sides. And now I got 2xa minus x equals 1. So you might be like, well, I can't combine these, so I'm stuck anyway. That's true. But what you can do is you can factor. Okay? So I can factor out an x, and I've got 2a here. If I factor out an x or divide an x by x, I'm left with a 1. So I've got 2a minus 1 equals just that lonely 1 on the other side. Now to isolate x, I need to get rid of the 2a minus 1. So I'm going to divide both sides by 2a minus 1. And then I'm left with my final answer where x is correctly isolated as 1 over 2a minus 1. Boom, done. All right, moving on. Here we go. factoring. Okay, and this is one way to solve a quadratic equation. Again, we're going back to that example earlier, x squared plus 5x minus 6, which we know how it factors. Once again, what multiplies negative 6 adds to 5, as Cole mentioned, it's 6 and negative 1. But how does this get us to our answer? Once again, solving for this quadratic equation, once we set it equal to 0, now we can say what zeroes out this and what zeroes out this. Oh, it's negative 6 and positive 1. So we've got our answer, negative 6, positive 1, boom, done. So this is one way we can solve a quadratic. We got another method, not my favorite, but it is an option. This used to be really handy and still is to some degree when solving for circle equation problems and trying to get into the right form. So completing the square does have a place, but now being able to use Desmos, that does help tremendously. But anyways, if you do need to complete the square to solve one of these, let me show you the steps. First, we want to get that constant to the other side. So I'm going to subtract both sides by 8, hence the negative 8. Then on the left-hand side, I'm going to take this b term, and I'm going to divide it by 2, which makes it 3, and square it, okay? And I'm going to add that to both sides. So again, half of the b term squared, and I'm adding that to both sides. Now we end up with a 9 in both of those positions, and 9 plus negative 8 is going to give us 1. That's fine. But the important thing is what we have on the left. What we have on the left is a perfect square. That's why they call this completing the square. What is x squared minus 6x plus 9 factored? Well, that's easy, right? It's x minus 3 times x minus 3. What two numbers multiply to 9 and add to negative 6? Negative 3 and negative 3. Hence this perfect square. And then we have a 1 on the other side. Well, now I can solve this pretty nicely, right? I can take the square root of both sides and destroy that radical. Not the radical, destroy the square, because the square root of anything squared is just the number itself. And then we take the square root of the other side, 1. And remember, it's not just 1 and negative. It's not just 1, it's 1 and negative 1. Hence the two equations. Now we solve these two equations, add 3 to both sides, and we get 2. Add 3 to both sides, and we get 4. And our two solutions are 2 and 4. Boom, done. By the way, you could have factored this at the beginning. You didn't need to complete the square. You could have also used quadratic formula, right? You have multiple options. I'm just giving you one of them. Cole says, where are you saying you can type in a non-completed square equation for a circle into Desmos, and it will still graph it? Yeah, I will show you. Actually, I'll show you right now. Hold on one second. Let's go Desmos. Okay. Let's see here. X squared plus 24x plus y squared. I don't know if this will be exactly right. Equals 24 or something. Yeah, see? It's right there. There's your circle. So you can do that. And the reason why, like, normally I'd say I'd complete the, let's say you're trying to find the radius, right? Hold on. Let's get it better. Let's see if we can get it better. Hold on. Let me try and do this in my head real quick. Hold on. 144, 64, 144, 64, 208, and what's the closest perfect square? 208, 225, so 17. So I'll set it equal to 17. Okay. All right, so let's say we have this as an example. And here, so you can see the full thing. So it's x squared plus 24x plus y squared minus 16y equals 17. And it's like, hey, we want to do our completing the square thing, get in standard form to, let's say, find the radius. Or you can just graph this and like, oh, what's the top point? What's the bottom point? Oh, yeah, it's at 23 and negative 7, right? Well, I know the diameter then. I just take the difference of 23 and negative 7. That's 30. 23 minus negative 7 is 30. Hence, the radius is 15. Or, you know, you could complete the square. I'm gonna take some shortcuts here, okay? I'm not gonna actually do the whole thing, but it's x plus 12 squared plus y minus 4 squared, or sorry, 8, y minus 8 squared, and then it's equal to 225. So you see it's right on the dot, right? So yes, you can get it into this factored form and complete the square and spend all that time, and then you'd be like, oh, radius is square root of 225, but you know, you don't have to. Okay. Cole, let me know if that helped. All right. Another option to solve a quadratic equation is using the quadratic formula once you've set it equal to 0. What is the quadratic formula when you got it in this nice standard form? You've got x equals negative b plus or minus square root of b squared minus 4ac all over 2a, okay? And, you know, what is A, B, and C? Well, A, again, color-coded, is that first coefficient. B is the second coefficient. And C is our constant. It's the standalone constant, okay? So let's plug everything in, right? We got -4 is B. So negative B is positive 4. B squared minus 4AC all over 2A. We simplify it out, right? 16 plus 8 times 16, 84, 128 is 144 over 4, 2 times 2. Square root of 144 is, of course, 12. So we get 4 plus or minus 12 over 4, which means our two solutions are 4 plus 12 over 4, which is 4, and 4 minus 12 over 4, which is -2. That's how you do it. Quadratic formula, boom, done. Okay. Moving along. Our next option is, of course, Desmos, right, which I just showed you guys. If we have the same quadratic that we just solved using the quadratic formula, you can also just pop it into Desmos. Look how I put it in there, just the exact same. And then you're looking for the x values. You might get these two funny lines. You're like, what is this? Those are your solutions. You just have to figure out the x value. The x values are consistent. The y values are what change. So if you're trying to get your solutions, you see, oh, it's -2 and 4 because that's my -2 is coming from that -2, and there's my 4. Boom, done. Okay. Now, another thing that might come up with solving a quadratic equation is having to determine the number of solutions of a quadratic. Or they might say, what's the value of this constant so that this quadratic has 2 solutions or 1 solution or 0 solutions? And those are the only 3 options, right? You can either have 0, 1, or 2. How do we do this? We do this using something called the discriminant. So let's say we've got it set up in this nice format. What's the discriminant? It is b squared minus 4ac. Now, depending on the value of the discriminant, we know the nature of the solutions, meaning is there 1, 2, or none? So let's talk about this. No real solutions or 0 real solutions. This is when the discriminant is negative, okay? No real solutions are where you get a negative value for the discriminant. That kind of makes sense if you think about where the discriminant is in the quadratic formula. It's under the radical. Can't take a square root of a negative if you want a real number, right? What about 1 real solution? This is when the discriminant is equal to 0. So if they're like, hey, find a constant such that there's only 1 solution, you need to set that discriminant equal to 0. Last but not least, when the discriminant is greater than 0, that's when you get 2 real solutions. And the equivalent when you're looking at a quadratic on a graph, 2 real solutions really means when it's going to have 2 x-intercepts, okay? Next, we get to number 8, linear and quadratic systems. So linear and quadratic. This is my line. This is my quadratic. And what are we talking about just from a broad standpoint? We're looking to see for those intersection points. That is our solution set, right? This linear and quadratic intersect in 2 spots. Hence, we have 2 solutions, 0, 3, and 4, -5. So that's what it means from a conceptual standpoint. Now, let's talk about how we actually solve these guys. So let's say we want to solve this system algebraically. What I'm going to do is I'm going to use substitution. Elimination, I mean, it kind of works, but really substitution is the way to do it when you have linear and quadratic, okay? So we're substituting for y. We're setting these 2 things equal to each other. Now we have one giant quadratic. So again, the goal is to set everything equal to 0. So I'm going to -3 on both sides and add 2x to both sides. This leaves us with this equation. X squared minus 4x equals 0. What are we going to do here? Oh, we got a quadratic. We just factor, right? No c term, so I'm going to factor out the x. X times x minus 4 equals 0, which means we have 2 solutions for x. Put it in the chat. What do you guys think of those 2 solutions for x? I'm going to give you guys 20 seconds. Go for it. I see Cole's got it in there, 0, 4. That is correct. Well done, Cole. And so we got 0 and 4, and those are our 2 solutions. But again, solutions are going to come in pairs, right? Coordinate pairs. We need an x value. We also need a corresponding y value. Well, to get the corresponding value, y value, you plug these values into either of these equations. I like to do both just to make sure. I plug in 0 to both, and I'm going to get 3. I plug in 4 to both, same thing. I get -5, right? 4 times -2 is -8 plus 3 is -5. That's how you do it. Boom, done. What about solving with Desmos? Well, this is pretty straightforward. And this is a really, really great option. Okay, sometimes the algebraic way might be a touch faster. You don't have to type it in. I mean, it's kind of up to you and your style and what you kind of figure out with practice. But Desmos is pretty slick. Watch this. Boom. Write them into Desmos, literally as is, and see the intersection points. Look at my solutions. 0, 3 right there. 4, negative 5 right there. That's how you do it. Done. Next, what if they say solve for C given that this system has one solution? Okay, very interesting. So first we're going to look at this algebraically. So here are my two equations, negative 2x plus C, and there's my quadratic. So again, solving it, right? We're going to set them equal to each other by substitution. Boom. And we're going to do the same thing that we did last time. We're going to subtract we're going to add 2x to both sides and subtract C from both sides. And then we've got this equal to 0, and that's ideal because it's a quadratic. We always want to set it equal to 0, zero product rule, right? Well, wait a minute. Now I got a quadratic, and they're saying they only want one solution. What does that remind you of? That might remind you, if we're talking about quadratics and talking about the nature of the roots, aka number of solutions. And Cole, I'm going to show you guys how to use the slide in a second. Great observation. But I like this, especially when it's hard to use the slide. Sometimes you might be getting like a weird fraction. I've seen it before. So this is bulletproof right here. But you can use the Desmos slider as well. So we're talking about discriminant. And when we have one solution, it means our discriminant for this quadratic needs to equal 0. What's my discriminant again? It is b squared minus 4ac. And it's got to equal 0 to have one solution. So again, b is negative 4. A is 1, C is 3 minus C, because the constant is 3 and negative C. It's both of them, not just one of them. All right, so now we have this. So negative 4 squared is 16, and then we've got minus 4 times 3 minus C. Let's distribute that negative 4. So we got 16 minus 12 plus 4C because the negatives cancel out. Now, as we combine like terms, we got 4 plus 4. 16 minus 12 is 4. 4 plus 4c equals 0, minus 4 from both sides. 4c equals negative 4. Divide both sides by 4, and we get c equals negative 1. Okay. Now, when Cole's talking about a slider, I think I showed on the next slide here. So now, if we're talking about solving the same thing, but now using Desmos, so watch this, same thing. Put it in as is, and here's your little slider, right? And you see how it said, do you want to add a slider for the constant? And I did. Moved it up and down until I got that one solution. Now, this is great when it's a nice whole number, not a whole number, nice integer, right? Like negative 1. So that's great. If it doesn't work out like that, if it's some weird fraction like 7/12 or 5/13 or something like that, that's going to be tougher to get on the slider. It could be a little frustrating. So especially if it's a free response question. So this is a surefire way to do it algebraically. But anyways, yes, that also works. C is equal to negative 1. Boom, done. All right, topic number 9 out of 13. We are moving on to radical, rational, and absolute value equations. Let's first start with radical equations. Radical equations are equations with radicals. Surprise, right? And here we have x plus 1 under the radical, and it's set equal to x minus 5. The main thing you got to remember, and by the way, you can also put this into Desmos. I'm going to show you how to do that in a second. It's pretty straightforward. But if you're doing this algebraically, the main thing to start with is like you got to kill that radical. Okay, and you do that by squaring both sides. So remember, you square a radical and you destroy it. What about the other side? Oh, I'm foiling it, right? X squared minus 10x plus 25. Now, again, we're going to use zero product rule. So we're going to subtract x and subtract 1 from both sides. Negative 10x minus x is negative 11x. 25 minus 1 is 24. We got this beautiful quadratic. We're going to factor, right? What multiplies to 24 adds to negative 11, negative 3 and negative 8. And my two solutions are 3 and 8. But now you have to verify something. When you're dealing with a radical equation, you have to check for what are called extraneous solutions. So we need to plug these back in and make sure they're good to go. First, let's try 3. 3 plus 1 is 4. 3 minus 5 on the other side is negative 2. And you might say, well, wait a minute. Square root of 4 is both 2 and negative 2. But when we're talking about these equations, we're only taking the positive root. So don't think that that this is also viable. This is not true. You're taking the positive root here. 2 does not equal to negative 2. That is a fail. But what about our second option of 8? Yes, we get radical of 9 equals 3. That is indeed correct. 8 is a winner. That's how you do it. Done. Okay. And let me just show you in Desmos, x plus 1 times equals x minus 5 here. Nice and easy. We get our single solution. Sometimes it doesn't show up. I don't know why it doesn't show up, but that you can see that that's on 8. So anyways, again, there's your value. All right. And what about rational equations? What's a rational equation? Again, you can type this into Desmos and get that answer. But in a rational, we're talking about something divided by something. Here's a quick example. How would we solve this algebraically if you want to do it quickly as opposed to typing it into Desmos? Do a little cross multiplication, right? 3 times x plus 4 on the equal to 9 times 4. Distribute that 3. We got 3x plus 12 equals 9 times 4, which is 36. Minus 12, 3x equals 24, and x equals 8. Okay. Again, you can put that into Desmos as well, but this is how you do it by hand, pretty quick. Last but not least, we got an absolute value equation. All right. Absolute value equations, once again, you can plug this in. I'm going to show you how to do it in a second. But the main way to solve it algebraically is to start by splitting this into 2 equations. First, the equation as is by just removing the absolute value bars. The second one, it's as is, but then we're going to negate what's on the other side of the equal sign outside of the absolute value and then just solve. Add 4 to both sides, we get x equals 10. Add 4 to both sides, we get x equals negative 2. What I've been seeing a lot on the practice test is they'll say, what is the positive solution to this equation? Or what is the negative solution? So you're going to need to solve it and then check it like so. Again, if we want it in Desmos, the absolute value bars are, you hit shift and that button right below the delete symbol. Right, x minus 4, was it x minus 4 equals 6? Yeah, it was, okay. Equals 6, and once again, we get those 2 solutions. We get 10, and we get negative 2. Again, it's not letting me click on it for some reason. I don't know why it does that, but there's your 2 answers. That's how you do it. Okay, we're on to topic 10, quadratic and exponential word problems. Now, we're going to get into quadratics and exponential graphs in the next 2 sections, which will flesh this out a little bit better. But in short, okay, we're talking about quadratics. There's a few things with 3 things in particular that are going to be important for these types of word problems, okay? Number 1 is the y-intercept, and that's our starting point or our initial value. So if they ever ask for, hey, how much did we start with or whatever, what was the starting height of the ball? That's our y-intercept. That's what you plug in 0 for x and you get it. The other value is the x-intercept or intercepts. Usually there's 2. In word problems, sometimes there might just be 1, depending on the usable zone of inputs. But anyways, that is the point of 0 value. If you have a quadratic modeling profit or revenue or whatnot, right? This is the point of 0 profit or 0 revenue. X might be time, X might be, I don't know, price or number of outputs, whatever it might be. And then the other thing is we have the vertex, which is the max or min value. Okay, so depending on if it's going up or down, opening up or down, the vertex is either going to be a min or a max. Okay, so now we look at these graphs, right? These are 2 different quadratics. This one's opening down where it's a max. This is opening up where the vertex is a min. And again, just so you can see, right, here are y-intercepts in red, the starting values. And we're talking about x-intercepts. It's where it hits the x-axis right here or here for this one. And there are 2 x-intercepts in both of these examples that could be likely relevant. And last but not least, the vertex or vertices, if in plural, right? The tops and the bottom. And that will be, they'll say vertex, they'll be referencing the vertex when they're like, hey, what is the maximum revenue? At what time do we reach the minimum profit, whatever it might be? And so just note, are they asking for the x value or the y value of that vertex in the word problem? Okay, we're talking about exponential. We've got a couple important things. We got the y-intercept in particular, same thing, starting point. We've also got the rate of change, okay? Now, this may not be so obvious from the graph, but the rate of change you can kind of figure out by seeing, all right, what am I multiplying the previous value to get the subsequent value, okay? That's usually my rate of change. And here when it's written out, right, this is my initial value out here. We're going to talk about this more in detail in later slides. This would be, the multiplier would be 1 plus r. But r itself would be that rate of change, meaning if r was like 0.7, right, it's increasing by 0.7 every time. If r is 3, okay, it's increasing by 300% every time. Increasing by 300% also means you're multiplying by 4. Just FYI. All right. And this is what an exponential graph is going to look like. And again, there's your y-intercept. It's where it hits the y-axis. Okay, moving on to the next section, quadratic graphs. And again, we mentioned what is a quadratic graph. It's going to look like this. It's a parabola either opening up or down. And once again, that's what it's called. It's called a parabola. Not that you really need to know that term. I'm just letting you know that that's what it is. And we have our standard form of a quadratic, which we've already talked about, ax squared plus bx plus c. Now, we know that this is a quadratic because, once again, the highest degree or exponent is a 2. All right? And that's what makes a quadratic a quadratic. If it's a 3, it's cubic, 4, quartic, etc. Now, in this standard form, we see we got a, b, and c, and what do those different values, kind of match up with? Well, my c value is always going to be my y-intercept. That makes sense because when you zero out x, you're just left with the c term, okay? And so that's something really easy and apparent that you can see straight from the graph here. Okay, what else can you tell when you oh, by the way, this next form is no longer standard form. This is intercept form. This is basically you factor it into 2 binomials. What does intercept form tell you? Oh, surprise, surprise, it tells you the x-intercept. So you can look at this and be like, oh, I know what the x-intercepts are. It's when these two go to 0, aka -3 and +1. So, oh, I have another mistake here. Wow, I am sorry, guys. Hold on. That should be the negative. It should be -3, comma 0. And it's fixed. Okay, my bad. Boom. Boom. So there we go, right? So you can see we got -3, 0. That zeroes that out, and we got +1, 0. And there we go. Does parabola ever open left or right on the SAT? Yes, it can open left or right, but no, not on the SAT. Never, ever, ever have seen that. So I don't think we'll see that. That would be x equals y squared, right? This will be a good question, Cole. That's opening to the right. This is not a function, by the way, because it fails the vertical line test, or x equals like -2y squared or something like that. Now it's going the other way. So otherwise, it kind of follows those same principles. We can shift it this way to the right or to the left and so on and so forth. Okay, and we've got one other format which is really important, which is vertex form. Okay, and this is a vertex form where h and k are the vertex. So in this case, and a just dictates whether it opens up or down, which is important, right? When a is positive, it's opening up. When a is negative, it's opening down. And we've got a vertex here at h, which in this case would be -1, and at k, which is -8. So my vertex is -1, -8, as I mentioned. That's how you do it, right? That's the beauty of vertex form. You can look at it and be like, oh, I know what the vertex is. Cool. All right. And in this example, we can see a couple of things. This first thing is negative, so that means it's opening down. We can also tell that the vertex is at +2, +3. Oh, wait. Oh my gosh, I'm having some major mistakes here. Hold on. So this is the wrong graph here. I'm going to show you the right graph. Let me get rid of this. Sorry about this, guys. Let's get rid of that graph. So I'll show you what this looks like. So +2 and 3, -2 times x minus 2 squared. +3. So is that what we had? Yeah. So if you look here now, right, we have that vertex at 2, 3, as I mentioned, and it is opening down. So there we go. Okay. All right, let's keep it moving. Finding the vertex. Now, this is one of the most important formulas on this test. If you're in standard form and you need to find the x value of the vertex, yeah, you could put it into vertex form. You could complete the square and do all that stuff. It's not so fun. Instead, there's a nice little shortcut. X equals -b over 2a. That gives you the x value of the vertex. So in this case, it would be -4 over 2 times 2, which is -1. And so we now know that the x value, the vertex, is -1. How do I know that the y value is -8? Because you can plug -1 in and see what you get for the y value. -1 squared is 1 times 2 is 2, plus 4 times -1 is -4, 2 plus -4 is -2, minus 6 is -8, -1, -8, boom, done. All right, now what about exponential graphs, okay? Talking about in our standard form, we have y equals abx. So what is our a value? A is our initial value, okay? It's also our y-intercept. When x equals 0, you're going to be left with a. B is the growth factor, is what I mentioned before, right? The 1 plus r. So that dictates, you know, how much it's changing from one to the next. So in this case, 3 times 2 to the x, this is something that's doubling every time x increases by 1. And we can see our nice typical format here. And this is a typical exponential going up to the right, exponential growth compared to decay. And once again, what's my y-intercept? As I mentioned, it's that a value 0, 3, and that's how you do it. And again, we're talking about growth in particular, where, as I mentioned, b has to be greater than 1. So we saw that last example, 2 is greater than 1. That was growth. A lot of times we're going to talk about exponential graphs in terms of percents. So if we have growth of 5%, b is going to be 1 plus that 5%, but in decimal format, aka 1.05. Here with this 10 in front, that's an initial value of 10. And once again, it's going up to the right. You see the y-intercept there at 0, 10, and you can see that it's, you know, it's growing gradually. But when x is 1, it's going to be up by 5%. 5% of 10, I think, is 0.2, right? Wait, what am I saying? 0.2. It's 0.5. Wait, what am I doing? 0.05 times 10. Yeah, 0.5, my bad. So that makes sense that right here we have 10.5. And yeah. What about exponential decay, right? We talked about growth going up to the right. Decay is the same thing, but b is now a decimal or fraction, something between 0 and 1. So for example, if we've got a 5% decay rate, now it's not 1 plus 0.05, it's 1 minus 0.05, aka 0.95. And then my b value is less than 1. So this is something like this, right? Initial value of 10.95. So instead of going up to the right, now we're going to see it going down to the right. And once again, my y-intercept is right there in red. That's 0, 10. That's how you do it, okay? Now we get to our final topic, polynomial and other nonlinear graphs, okay? We're getting close to the end of this presentation, so make sure if you guys have questions, put them in the chat and we'll answer them before we conclude. All right, so polynomial and other nonlinear graphs. Polynomial graphs, okay? Just as an example for this cubic. Oops, where's my graph? There's my graph. All right, those timestamps were a little off. So we have this polynomial that we looked at before in factored form. Again, we know that the zeros are where when these zero out, right? So we have 1/4, we have 2, and we have 3. Now, if we look at the graph, those zeros are apparent, right? We see the 1/4 0. We see the 2 0, and we see the 3 0. So that's how it manifests on a graph. Now, the one thing that's not on this visual that I do want to mention is, what about if we see a 0? Let's pretend that this thing came back up and it bounced. It didn't go through the x-axis, okay? Let's say the graph now went here, and then we have an x-intercept at -1/2, 0. But it doesn't go through, it bounces. What does that mean? When it bounces versus penetrates, right? These are penetrate, penetrate, penetrate. Penetrating, meaning going through, should have an odd degree, usually a degree of 1. Notice all of these binomials have a degree of 1. But when we see a bounce like this, it's an even degree. Now, on the SAT, I wouldn't think of anything other than 2. It's probably just going to be 2. But what that means is, you know, what would the binomial that gives us a 0 at -1/2? It would be 2x plus 1, right? -1/2 times 2 is -1 plus 1 is 0. But we shouldn't expect to see it like that. Since it's bouncing, we should see it to the second power, okay? Let me show you this quickly in Desmo so you can get a better idea of it. So let's say, for example, we have... Actually, let's do this exactly. 4x minus 1, x minus 2, x minus 3. 4x minus 1, x minus 2. Okay. So here is the example, right? It's the same graph as I mentioned. Now, what did I say? 2x plus 1. Now, if I don't square it, notice how it goes right through. Let's see if we can close this off a little bit. So you see it goes right up, but then watch this. As soon as I square this, now you see that bounce. You see how it bounces and goes down. So anyways, when you see a bounce, you know that that binomial that's being zeroed out, it has to be to the second, or technically the fourth or sixth or whatever, but usually second power on the digital SAT. Okay, what about rational graphs? I've talked about this on my math formula video. We talked about this a couple weeks ago, but I'm going to go over it again. So rational graphs, again, it's a rational function, meaning something divided by something. There's important things that you need to be aware of when you see a function like this, right? Here's what the graph is going to look like. And where do these numbers in red and in green come in? Well, the x-intercept can be figured out from where the numerator zeroes out. So since it zeroes out with a 4 minus 4, the x-intercept is at 4, 0. What about the denominator? I see x plus 3 on the denominator. Where does that zero out? At negative 3. That tells you where the vertical asymptote is. What is the vertical asymptote? I don't see anything at x equals negative 3. It's that invisible barrier, that vertical invisible line at x equals negative 3 that splits up those two different pieces of the graph. And last but not least, we have 0 over negative 4/3 for the y-intercept. Where am I getting that from? Oh, negative 4 over 3, right? It's what's left when you plug in 0 for x. So we get that y-intercept at 0, negative 4/3. That's how you do it. Okay. One more example. We got x plus 2, x minus 5. So again, here's the graph. What is the what is the, what am I asking here? Oh, is this not on here? Wait 1 second. What's up with this graph? No, this is right. I want to ask everybody first, what is the x-intercept here? So I'm going to wait until I see some answers. Somebody give me that x-intercept. Oh, Cole's asking if it bounced, would that count towards how many times does f of x equals 0? Great question. Cole, that's a great question. Usually what they'll ask on these problems is they'll say, how many unique solutions or whatever does this have? So when you have that's the second or third or fourth power, that's your multiplicity of 2, 3, or 4. So technically, it increases the number of solutions. But every time I've seen it asked about in the digital SAT, they're talking about the unique one. So even though it's squared, it's still the same value twice or 3 times or 4 times, right? If it's to the third or fourth power. Great question. Osama says, and so does Cole, that we have an x-intercept at negative 2. And that's correct because that's where we're zeroing out the numerator, right? And you can also see it right there. There's our x-intercept at negative 2. We got the x minus 5. That means we have a vertical asymptote. Where? Where do we have a vertical asymptote, Cole and Hassan and Osama? Vertical asymptote, vertical asymptote. Cole's got it as x equals 5. That is correct. It is x equals 5 because that's where we zero out the denominator. Last but not, and there's our invisible vertical asymptote. Last but not least, we've got our y-intercept because when you plug in 0 for x, right, you get 2 over negative 5, hence negative 2/5. There's our y-intercept. Boom, done. Ladies and gentlemen, that is it for our lecture today. Go ahead and ask your questions if you got questions. Once again, thank you guys so much for all of the likes. We got a lot of likes in today for the people that joined. I really, really appreciate it. I know it might not seem like a big deal, but when you do like the videos, it makes a big difference. It really helps to push the content and promote it. And again, this is all free for the world. I'm just hoping I can make the best content possible so people can do the best they can, the best they can on this test when we're taking it in August or thereafter. So please make sure to definitely click that like button, put some comments in. I'm going to add our digital SAT class on school once again for all you guys who have not joined yet. Here it is in the chat. Please make sure to sign up because this is where you can get the slides for this if you want them. You can rewatch the lectures. You can see our schedule for when you're supposed to take tests. We've also got all these practice problems that I'm uploading. I'm in the process of uploading all of them right now. Practice problems tied to each individual practice test, which are going to be super, super helpful. You can be like, oh, I got question 3 wrong on practice test 1, module 1. Here are 5 iterations of that question, let me rock them out and get some good practice. So make sure to do that as well if you haven't signed up yet. Cole, you're very welcome. And to everybody else who has joined today and joined on along in this journey, you are all very, very welcome. And I am thankful to you guys, because the more of you guys that participate, the more people we can help, the more we can spread the word and all that good stuff. And last thing I'll say, if you guys have friends that are looking for SAT prep, maybe they already have a tutor or a class that they're a part of, but I would still encourage them to join this class, because as I mentioned, this is the best of the best. And I think we got amazing verbal content every Thursday, amazing math stuff every Tuesday, stuff that I've been working on for years and years. I've been at this for a long time. All right, guys, I don't see any questions coming in, and my dog is crying. So I'm going to jump off, but thank you guys so much for joining. I really appreciate it. Once again, thank you for all the love and support over the years. I really appreciate it, and we will see you next Tuesday for a math class once again, and that is it. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.